So you have got a coordinate system. Cartesian means scale of units is same on three axes. So if you have got meters, it is meters on all of them. Same units, same scale. Now this is a right-handed coordinate system. It can be right-handed, left-handed. What is the meaning of right-handed coordinate system? If you take x-axis to y-axis,
Excuse me, sir. Sir, your screen is not visible.
okay, I'll do. So now it is visible.
Yes, sir.
So
Yes. Yes.
if you take
Yes, sir.
x-axis to y-axis, you see, you have to rotate the screw counterclockwise. Going from x-axis to y-axis involves counterclockwise rotation. If you have a right-handed screw, it will come towards you in the direction of z-axis. But suppose your coordinate system was left-handed, then what would happen? Your z-axis will be pointing into the plane of the board, into the plane of this page. It is going into it. So that would be your positive sense of z-axis. So this is a left-handed system. Here you are having a left-handed screw. If you go from x to y axis, it is a counterclockwise rotation, and a left-handed screw will go into the plane of the board. So it becomes a left-handed coordinate system. We generally use a right-handed coordinate system because vector cross product is defined for a right-handed screw. If this is your direction I, this is your direction j, then I cross j is equal to k. And this is your direction k. So that is defined for a right-handed coordinate system. And k is pointing towards you. Had you used a left-handed coordinate system, your I cross j would have been equal to minus k. Because I cross j has to point in this direction. And while your positive z-axis is other way around. So this direction will be minus k of this axis. Okay. So for left-handed coordinate system, your your product rule, cross product rule changes. Your vector product is different. So this is known as cross product or vector product. So we always stick to right-handed coordinate system so that we don't get into the problem of sign. So it makes your life easy. Okay. Another thing I generally like to talk is dot product of two vectors. You take two vectors u and v. I, j, k are the unit vectors in direction of x-axis, y-axis, z-axis. That is very standard stuff. So how do you find unit vector? These are also known as basis vectors. You have a coordinate system. You can reach any point in space with the help of basis vectors, that is vector in direction I, j and k. So these are three basis vectors. When I put a bar below something, it means a vector. One bar below it. So you can say your dot vector u is has components u1, u2, u3. Vector v has components v1, v2, v3. What is dot product of these two vectors? You all know this. But you can also write it like here I is a repeating index, also called a dummy index. So this is a shorthand notation for this entire expression. You can write it in shorthand like this. So this notation was introduced by Einstein. This is also known as Einstein's notation. Suppose you have a matrix, you have a equation y is equal to ax. So this is a linear transformation. So what are the properties of a linear transformation? Zero will be mapped to a zero. So zero of this will go to a zero of this. So you have transformed a vector x to a vector y. So you can write it as y1, y2, y3. This is a matrix A. So this matrix A transforms this vector x to vector y. If it is all zeros, you will get a zero answer. So this is a very important property of a linear transformation. Zero should map to a zero. Zero vector should go to a zero vector. If it is some other vector, suppose you have a vector like this, it can be transformed to another vector. So what has happened? You have rotated the vector and changed the magnitude of vector. So these are the two things that happen to a vector once you do a linear transformation to it. Rotation and change of magnitude. If you just change only the magnitude without rotating it, suppose you have a vector, I take I take some matrix like this. So I am taking just a two-dimensional matrix. So if I take a vector 1, 0, what is the answer? It will get mapped to what? You see, so you had a vector which was along x-axis. Now you have rotated it. So you see, you have changed the magnitude. Its magnitude is root 2. Earlier it was 1, and you have also rotated it. So two things happen. Suppose you had a vector instead of 1, 0, you had a vector 1, 1. Then what happens? Your answer becomes 1. You get an answer 2, 2. So it means you just increase the magnitude by, you double the magnitude. Your input was this, your output is just double of it. So such vectors are known as eigenvectors. Eigenvectors correspond to this matrix. So this matrix will transform eigenvector by only change of magnitude. It will contract or stretch the vector. It will not rotate the vector. So these are some very basic stuff. I generally like to talk about them. So how do you write it in index form? Y is equal to Aij xj. So this is in index form. So what is y1? You see j is a repeating index here. So whatever repeats has to take all the three values. All three values 1, 2, 3 it will take. So how will you expand if you put a y I is equal to 1? If you also just expand it, a11 x1. If you just expand this row, a11 x1 plus a12 x2 plus a13 x3. The same thing has been explained by this rule. So this is a rule coming from this matrix y is equal to ax. In component form, you can expand it like this. Similarly, y2, y3. So you have got three equations. You see, this statement gives you three equations, and you have shortened a lot. So that is the advantage of this notation. You can write in long, write in short, a long equation. Okay, now let's come to Newton's laws. So first law defines an inertial frame. So you can say only that something will stay in a state of rest or uniform motion if your observer is in inertial frame. If you're not observing the phenomena from an inertial frame, you can't say that. So either your observer is at rest or uniform motion. Observer is not accelerating or rotating. Okay. Okay. Now, second law, F is equal to ma. So here m is the mass of the particle. The force F is the force applied to the particle. So how you can write is that m dv by dt. So v is nothing but dx by dt. So x is the position of the particle. It is a position vector. So when I say x position vector, it has got coordinates x1, x2, x3. Instead of x, y, z, you can write x1, x2, x3. So it's a second order differential equation. If you want to solve it, you need two initial conditions. If it was first order, you would have needed one. Since it is a second order differential equation, you need two initial conditions. And what are those initial conditions? Position at time 0 and velocity at time 0. All right. Once you know these initial conditions, you can find position and velocity as a function of time. You can map the trajectory of the particle, where it goes. So if you write the trajectory at each point of it is at particular time you are having different positions. So in this diagram, time is hidden. You know, once you have a time, you know the position. So that you will build up with the help of initial conditions and equation of motion. This is also called equation of motion. Okay. Third law, all of you know, action and reaction are equal and opposite, and they act on different bodies. It kind of gives you the characteristic of force. Now you have many particles. Then you have to apply these equations to each particle. So as many particles, as many differential equations. So you got n particles, so n differential equations, and 2n initial conditions. So for each particle, you need position and velocity. Now suppose you have a rigid body. That is one standard case. So how do you define a rigid body? Anybody? Yes. Are you guys there?
Yes, sir.
So how do you define a rigid body?
If we take any 2 points or any two random points on the body and body moves, the distance between the point remains the same.
Okay. Basically, interparticle distance is constant. So that is the constraint of a rigid body. So it is like a many particle mechanics, but you cannot change the interparticle distance. So what happens? Degrees of freedom, which were like 3n, like position of the particles. As many particles, so many position vectors you needed. Now that degrees of freedom gets reduced to 6. What are those 6 degrees of freedom for a rigid body? Suppose you have a rigid body. You take any arbitrary point on the body. On that, through that arbitrary point, you can pass a coordinate system. So this is your coordinate system. So what do? Choose an arbitrary point. Define a coordinate system. Embed it with the body. So this is known as body coordinate system. And then you have another reference frame. You call it lab system. Now body is going around in space, turning around, rotating, translating. Then what happens? One thing you need is position of this origin. So you need position of origin of body coordinate system. So you can talk of this position with respect to this fixed lab system. So how many degrees of freedom are involved? So this position of the origin will involve 3 degrees of freedom. X, Y, Z coordinate of this origin with respect to this lab system. Number 2, what are the other degrees of freedom you need? You take any point in the body. As
Noted.
this coordinate system, body
Sir,
coordinate system is rotating. Yes.
sir, rotational and vibrational.
Okay, we'll get to it. So this point is fixed with respect to this coordinate system, embedded system. If you know this coordinate system, you know position of every particle. So position of every particle doesn't change with respect to these lines. Particle may body may travel in space, it can rotate around, but position of each of them is fixed with respect to this system. Its coordinates are not changing with respect to the embedded coordinate system. So if you can tell the position of origin and the orientation of these lines, if you know the orientation of body axis, if you know these two things, you know position of each point in space. So this you know with time, what is happening to these two things. Then you can talk about, you can tell position of every particle of the body with time. So how do you define orientation of these axes? How many degrees of freedom are needed? So this is a vector. How do you represent a vector? First thing. How do you represent a vector? Yes, anybody? So this is a vector V. So what you can do is you can represent the vector by its components. That's the best way to represent a vector. So how do you find components of a vector? You take the dot product with these x unit vectors. You take the dot product with the 3 directions, these unit vectors, and you will get to know the component of the vector. So V1 is what? Vector V dot I. Component V2 is vector V dot J. Component V3 is vector V dot K. So this way you get components of 3 vectors. Component of 3 components of the vector. Suppose you have a unit vector. So what unit vector? So what is the meaning of unit vector? Magnitude is 1. Then there is a concept of direction cosines. So what is the meaning of direction cosine? You have a vector v, take its dot product with I. What do you get? Magnitude of v, magnitude of I is 1. Angle between v and I is theta, cosine of that. If magnitude of v is 1, then you get cosine theta. So this dot product gives you direction cosine. So you get angle of vector v, cosine of the angle of vector v with x-axis. So this is your first direction cosine. If you get v dot j, so you will get cos of, usually we determine with, call it alpha, then v dot k will be cos of gamma. So you have got three direction cosines. Cos alpha, cos beta, cos gamma. So you can represent your unit vector v. For unit vector v, put a cap. So what is the restriction on it? So how many degrees of freedom it has? Only two. Once you know alpha, beta, gamma is immediately known. So you have got 2 degrees of freedom. You see, you have got an embedded body coordinate system with the body. You first want to define its x-axis. It is a vector direction, unit vector I. Now you have only 2 degrees of freedom for it. If you know alpha, beta, the angles it is making with the your in fixed coordinate system or lab coordinate system. So this was a fixed coordinate system. So you can define this axis by the angle it makes with XYZ axis. So you need 2 degrees of freedom to do it. Then you need y-axis. It is perpendicular to this. So if you take a plane perpendicular to this x-axis, your y-axis will be defined, will be any line in that plane. So you have a restriction on this y-axis that it has to be perpendicular to this x-axis. Y-axis can be again arbitrarily defined by 2 degrees of freedom, but it has a constraint that it is perpendicular to x-axis. So I dot j is equal to 0. If two vectors are perpendicular, their dot product is 0. So what is the degrees of freedom for y? Only 1 degree of freedom. So once you have no x and y axis, z direction is given by right hand rule. So it is automatically defined. You take x axis to y axis, z axis will come out of towards you. So it gets automatically defined. So you need only 3 degrees of freedom to define the orientation of the body axis. So you have got 3 degrees of freedom for the origin of the body coordinate system, 3 degrees of freedom for the orientation of the axis. So this way you have 6 degrees of freedom of a rigid body. So how do you define the motion of a rigid body? It is going around in a space, rotating with respect to the fixed coordinate system. You just tell the position of the origin and how this orientation is changing. And you are done. And you have defined fully the motion of the rigid body. So all this you can see if you go to my YouTube lectures. So there I have done all this in greater detail. And there is something called Chazel's theorem, another important theorem in mechanics. What does that theorem say? A general rigid body motion is superposition of pure translation and pure rotation. So you have any general rigid body motion, it can be treated as sum of pure translation. So what you do, take any arbitrary point on the body. This is the final position of the arbitrary point in this body. So you give the entire body translation corresponding to translation of this point. So your entire body comes here. So here you have just translated. Pure translation means displacement of every point on the body is same. It is the same vector for translation. Now you rotate the body about an axis passing through this point and you reach this configuration. So this is a case of pure rotation. You have rotated the body about an axis and the entire body has rotated about an axis passing through this point and you have reached the final configuration. So you don't have to analyze a general rigid body motion. You split into two parts, pure translation and pure rotation. You see it is easy to understand and analyze pure translation and pure rotation. So what you have achieved, just do superposition of these two processes. If you had taken another point as, suppose you had taken this point, now you give the body translation corresponding to this point. Now this point has gone here. Now you give entire body translation corresponding to this point. So what happens? So this body takes this position. If it translates with this vector, now it has to come to this shape. It has to turn like this. If it turns like this, you will like acquire this orientation. This is your final orientation, final configuration. Now you see, you will find that these two angles of rotation are same. You see, what is this sense of rotation? Counterclockwise. This is also counterclockwise. So you will, this is one important thing. The translation vector depends on choice of reference point. In this case, translation vector was different. In this case, translation vector was different. But amount of rotation remains independent of choice of reference point. So these are two important points in Chazel's theorem. So what is generally done is we choose reference point as the center of mass. Centroid is generally chosen as the reference point. So it makes your equation simpler. Then you say any force is acting on the body that is equal to mass into acceleration of the center of mass. And you find the position of center of mass with time, how it goes around. Because you know initial position of the center of mass, you know initial velocity of the center of mass, and you know the forces. So you can find trajectory of the centroid. Then there is this is equation of translational motion. Similarly, you can write equation of rotational motion. So there you have R cross F, or torque of the applied forces, is equal to time derivative of angular momentum. So here you have taken this R, this movement of forces about the centroid. So this angular momentum of the body is also about the centroid. With these two equations, you are able to find the, so this it can be simplified to I alpha. Alpha is angular acceleration of the body. This is moment of inertia tensor. So you will learn what is moment of inertia tensor. I don't know if I will like to talk about this in this course, but it is all there in my YouTube lectures. If you look at it, you can go through it. So once you know angular acceleration, so if you know initial configuration, initial orientation of the axis, then you can know how the x direction of the axis will change with time. One more thing is the concept of, hello, He- hello, बैंक में आपसे मैं शिवम बात कर रहा था दिल्ली से एक्चुअल मैंने पर्सनल लोन की रिगार्डिंग आपको कॉल किया सॉरी नॉट ऑल okay. So another concept is of fixed vector, free vector, sliding vector. So these are important concepts. What is the meaning of fixed vector? Fixed vector means, so suppose we talk of force. So force has got three important concepts with it. Number one, magnitude. Number two, direction. Number three, point of application of force. So if you have a body, you apply force somewhere here, then what happens? At this point, it will feel some pressure. You are applying force here, it won't feel pressure here. It won't feel pressure here. So when you want to do stress analysis, then force is a fixed vector. You cannot move the force. You cannot say force is here or here. You will say for stress analysis, you will treat force as a fixed vector. Its point of application of force is very important. Another thing is sliding vector. What is the meaning of sliding vector? You can slide the force along the line of action. You can slide it anywhere. Then you can analyze its rigid body mechanics. Its rigid body mechanics will not change. For example, force is applied, you have applied applying forces like this. If you want to find the net force, you can find the net force by parallelogram law. You move the forces along its line of action, they are intersecting here, and now you find its resultant force by the parallelogram law. So this is a net force due to this. Now these two fellows are there. Now you try to make them intersect. So this is your this force, this is your this force. So net force will be, so this becomes your final resultant. So now what is the acceleration of the body due to these forces? It will be in this direction. And you have found the resultant by translating the forces. So if you want to do the dynamics of the body, you can treat it as a sliding vector. And when it is a free vector, what do you mean by free vector? Suppose you have two vectors A and B. How do you add them? You can just take them parallel to itself. If that kind of a thing is allowed, then it is a free vector. Now rotation is a free vector. You could have taken any point in the body. Body takes this shape, this configuration. You have translated it with this position. Hello, somebody is asking it is fluid mechanics or mechanics. So please, it is the basics. Unless you know the basics, you can't build a good framework. You need a strong foundation. Okay, so bear with it. I like to put people on a strong foundation. So rotation is a free vector. So I know these basics looks basics, but you may not be knowing all of it. That is the idea. So okay, Diksha, now I'll ask you questions. What do you understand by rotation of a body? What do you understand by rotation? Suppose you have a body rotating about an axis passing through this point. Can you tell me where will this particle go from here to here if by some rotation delta theta is there? Okay, one person has left the meeting. Not an issue. Okay. So if you have got this vector r, then this vector is known as delta r, and this you will know is delta theta cross r. Okay. So this is little advanced stuff. Delta r is equal to delta theta cross r. So here, by process of rotation, this tells you the displacement caused due to process of rotation. Okay. So meaning of free vector is you take any line in the body, if it rotates, This line will take, suppose, this position after rotation. Take any other line in the body, it will suffer the same amount of rotation if it is a rigid body. Amount of rotation is independent of position. You will define only one rotation for the body, only one rotation. You cannot say there are two rotations in a rigid body. While if you take any point in the body, suppose you take this point, body travels to another position. This is a one vector. Any other point in the body, it may suffer a different amount of displacement. So translation is a fixed vector. It depends on the position. It is different for different positions. But if you had a pure translation, entire body has a pure translation. Now displacement as a vector is same for every particle. Okay. So in this case, your displacement becomes a free vector. But for a general rigid body motion, rotation is a free vector, while translation is not a free vector. That's a fixed vector. Okay. So some basics. Now rigid body mechanics, why is it so important? Why is rigid body mechanics? Anybody? Number one is you have uniform translation. Number two, you can talk of translation. Number two, rotation. So what happens during these two processes? There are no strains in the body, no stresses. So why are stresses and strains connected to, why do you not have any strains and stresses in a rigid body motion? Anybody? So rigid motion, no strains and stresses. Yes? Anyone would like to answer?
Because the whole body is moving with the same speed.
Okay. Now what is the meaning of rigid body motion? No change in interparticle distance. What do you understand by a crystal? So you got particles, atoms in their lattice positions. So why do we have solids, liquids, and gases? Anybody? Yes. Yes. What is the answer? Why do you have solids, liquids, and gases? So it is because of the intermolecular forces. So In solids, they are stronger. In liquids and gases, they are weaker. So there is a concept of cohesive energy. So what is the meaning of cohesive energy? If you take a crystal, for example, okay. First, I like to talk of Leonard Jones potential. Have you heard of it? Anybody?
No, sir.
No, sir.
Okay.
No, sir.
You have got two atoms, for example. So potential energy between the two atoms is a function of their interatomic distance between the two particles. And you will find that this thing goes like this. So this is the position of minimum potential energy. And this is known as equilibrium distance. So when the two particles are very far apart, they don't feel each other. Their interaction is zero. So you say the interaction potential energy is zero. If they try come closer, you see their potential energy is becoming negative. So potential energy is reducing. So this is like an attractive potential part of the potential. If you try now, this is their equilibrium distance. Now their potential energy is minimum. If you want to take them closer, then you have to apply force to bring them closer. And this is known as repulsive part of the potential. If there was no repulsive part, then what will happen? Yes. Why do you have this repulsive part of the potential? Then all matter will collapse to a point. So why do you have this repulsive potential? You heard of Pauli's exclusion principle in physics. So no two electrons can have the same set of quantum numbers. So you try to bring them to one position, you are violating this law. So this makes them, that is why material has got bulk modulus. It refuses to get compressed. So you have to spend energy to reduce the volume further beyond this point. So if you have atoms, they will try to arrange themselves in such a way to minimize this potential energy. And this Leonard Jones potential was defined for ideal gases. So initially people found it for the helium, neon, etc. What is the potential energy of interaction? You see, even they don't have zero potential energy of interaction. There is some potential energy of interaction. Only then they can be liquefied. If there was zero potential energy of interaction, they will never be liquefied. But if you have got different materials like iron, nickel, they have got their different sets of these potential functions. And these are found by quantum mechanics. So they are very elaborate functions. So all that is found by quantum physics. So that's a property of that material of iron, nickel, whatever you have, it will have its own potential energy function. And that decides the crystal shape of the particle of the material. The crystal shape, whether it is a FCC, BCC, whatever is the structure, because of a certain potential energy functional, it will acquire this shape, this structure, because in this structure it is minimum. Okay. So why do you have strain energy? Because you're disturbing the atoms from their equilibrium position. Suppose this is the equilibrium position of the crystal. Now you apply some force. So this particle goes this distance. So they move. So you find that this length, this lattice parameter has changed because you applied some force. So whenever you disturb a structure from its equilibrium position, then you have to spend energy. Now it has higher interaction potential. This potential energy is a function of distance. So suppose you want to find potential energy of this function, you have to find all the neighbors, nearest neighbors. And there is a potential energy of interaction between these two atoms. Similarly, between these two atoms. So you add up all the potential energy and you will get potential energy of interaction between these atoms. So if you change the interatomic distance, that potential energy will change. You need more energy. Now the system has got more energy. So this is strained, it is in a higher potential energy or higher strain energy. And from that, you can also define what are the stresses, what are the strains. Okay. So we have why we have stresses, because we have the body disturbed from its equilibrium state. Okay. So in rigid body motion, you don't change interatomic distances. So you don't change the potential energy. So you don't have stresses and strains. So that is very important. Suppose you define some function which tells you the energy in a different configuration, then you have to check it out. Whether that configuration, if it is resulting from a rigid motion, it should not have any change in its potential energy. There should not be any stresses associated with it. Okay. So we always try to check it out. And this you will find useful in fluid mechanics also. That if you have a pure translation or pure rotation of a fluid, it should not develop stresses. Your formulation should be such that stresses should not be seen. So we had talked about potential energy. Okay, I was talking about cohesive energy. What is cohesive energy of a crystal? You take a crystal. Okay. Now you repeat it. Okay. And then what you do, you find energy of each atom. How do you find energy of each atom? See, it is interacting with so many fellows. You find their interaction energy. Each of them you take and find their interaction. So what you will find, suppose it has got n atoms in a crystal, you find its interaction with everybody. So you will find that every interaction is being counted twice. This fellow is interacting with it. When you consider this fellow, This is also interacting with it. So you're counting it twice. You find the total energy of interaction, divide by 2. So that will give you potential energy of the system. And suppose your atom, whatever crystal you took had 1,000 atoms. So you take the total potential energy, divide by 1,000. So you get cohesive energy per atom. So what is the meaning of that cohesive energy? If you provide that much energy to the crystal, you can break it apart. So this is the energy which will be released when these many atoms are brought together. So that is a reduction in their energy. You see, it goes from, if no all atoms are far apart, energy is zero. You bring them together, they set into a crystal. For setting into a crystal, it has to be in the dip in this curve, which I just showed you. So their potential energy is now reduced. If you provide that much potential energy to it, that much energy to it, so you can go from negative to zero, and that is known as cohesive energy per atom. You can calculate this way. So you will find this energy is of the order of some electron volt per atom. For different materials, it is of a different value. So this is something called, you will see, a microscopic concept. You know about microscopic and macroscopic properties. So it's a microscopic concept. When you talk of cohesive energy of an atom, then similarly there is a surface energy. You can also define surface energy of different materials. So that is also defined electron volt per angstrom square. Or you can even talk joule per meter square. So what is the lattice parameter generally of the order of 3 to 4 angstrom? So you have got some atoms. Why do you have surface energy is higher than cohesive? Why is an atom at the surface having more energy than atom in the bulk? Anybody? Why an atom in the surface has higher energy than atom in the bulk?
Because sir, it is not because there the forces on it are unbalanced.
Always
So the
there is a balance.
atom in the bulk are
Yeah.
surrounded all over by the other atoms.
Okay. So atom at the surface has less number of neighbors. So its potential energy reduction is less. So that is why we say it is in a higher state of energy. While atom in the bulk will have more number of neighbors. More the number of neighbors, more interaction potential becomes negative. That is in lower energy state compared to the surface energy, surface atom. So surface energy, you can also find, you take the atoms on the surface and you find their interaction with their neighbors. So their neighbors will be only on one side. So we can find surface energies of every material. Okay. So this is a microscopic concept. So what do you mean by macroscopic concept? Yes.
So it deals with the molecules on the molecular level.
Okay. So what is happening is, you see, any material, you are not having small number. You have large number. So you don't have small numbers. You have got large number of atoms, large number of particles. I just told you 32 gram of oxygen has Avogadro number of It's a very big number. So whenever you have large numbers, you talk of macroscopic property. You cannot follow each particle. So what you will say, you take a number of particles when the number becomes substantially large, and you can define some kind of an average property. I'll give you an example of density. Suppose you catch one atom. Then what is the density of that atom? So mass upon volume of that atom, and you plot that density. It is some large value. Now you try to catch another atom. Now you have a ball here, two atoms. Now the density will change. You have got some fluctuation. Then you catch the third atom. Now you find the ball containing these three atoms. So you'll find that density again changes. So you'll have fluctuations. Now you have got many number of atoms. You find their neighbors. Now you'll find, now suppose it is having 1,000 atoms. After what, if you want 1,001, so now you will find that your density is kind of stabilizing. So when you reach that kind of a scale, that you have a stability. But again, you can have variations as you go further and further away, make the things much larger. So here you have an asymptotic value of density. This is your density. This is your number of particles in the ball. So here you can define it as a macroscopic property. So you're not worried about that fine the fluctuations here. You define density, try to reach, you try to make a group of atoms, reasonable number. Now you have a big volume of area, room, for example. You see there are large number of molecules in it, maybe at the order 10 power 30. Now you make small partitions in it. Now even if this partition is small, it may be having a very large number of atoms. You make further partitions. Still it will be having very large number. So each of them is having a large number of molecules or atoms. So how do you define energy of the entire room? Sum of the energies of each partition. And each of them is also very large. So that is the way of describing macroscopic properties. You have a system. You can define overall energy of the system. And you can also define these microstates. And you can also talk of their properties in an average manner. So their energy, you can call it internal energy. You can call it temperature. You can call it pressure. So these properties can be defined even of these smaller subsystems. This is one big system. These are the smaller subsystems. Even they are of such a large scale. Okay. Okay. I think some fellows are feeling disturbed unnecessarily. Let me talk of something different now. Let me talk about little bit of fluid mechanics, because once I will get into more details of it, I'll need a bit of fluid mechanics also. So what is one thing is called Eulerian description. Second thing is Lagrangian description. So another thing is called field. Have you heard of this word field? What is its meaning? Anybody? Yes.
Things experience force in a field.
Faith. There's a region which is affected by a
Field is
force.
distribution of a quantity over space and time. If you define any quantity, describe it values over space and time, it is called field. Temperature field, pressure field. Okay. What do you mean by Lagrangian distribution? You give, suppose, position of a particle. Position and velocity. So you have a body, you give position of each particle with time, how it is changing. So you give description of each particle of the body. But suppose you have a fluid, pipe flow. Now you can't, you've got an infinite number of particles and they keep changing all the time. Water is entering from here, leaving here. So there you can talk of position and velocity in space, spatial description. You don't talk about each particle. You say this is the position, this will be the velocity. You describe velocity as a function of position
Sir,
and
can you
time.
write with a black pen? It is not visible clearly.
Okay. So velocity you give as a function of position and time. So suppose my particle is here at this time, this is the velocity. Now my this same particle has come here. So I will assign the velocity corresponding to this position and time. So this is a spatial description. You're not telling velocity of each particle. Some particle has come, particle has gone. You can't be chasing them. You just tell the velocity as a function of position. Is it all right? Okay. So this is known as Eulerian description. This is known as Lagrangian. Suppose I give a function Lagrangian description. I give position vector with time. So how do I find velocity of the particle? I said, so this will give me velocity of the particle. Now I have an Eulerian description. So I give the velocity description as a function of, and what is the acceleration of the particle here? Because you are giving the velocity variation as a function of time. So you can just directly take the derivative with time, you get the velocity. And how here you will calculate the velocity? Now see, velocity is changing with position. Okay, I'll tell you, not this way. Now this is, we want to find, how do we find derivatives? Have you heard of Taylor's theorem
Yes,
in mathematics?
yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. If it is in a single variable, so you have seen this equation? Yes? Have you seen this?
Yes, sir.
Yes, sir.
Is it an exact
Yes,
statement?
sir.
Sir, approximation.
No, sir, exact.
So why do you use this Taylor's theorem? What is its application? Yes.
Sir, complex polynomial can be solved by using this.
So to approximate a function.
Suppose you have a function point here. You have a continuous function. If you know the derivatives at this point, if you know function value, its derivatives, then you can find the value of the function in the neighborhood. So this is known as the local description. You define function value and derivatives at a point, then you can find the function value in the neighborhood. That is the use of this theorem. Now I'll just take a simple case of a polynomial. What is f prime x? 2x. All higher derivatives are 0. So if I say so at fx, at value x, at it is fx is equal to x square plus h. First derivative is 2x. Second derivative is 2. All the other derivatives are 0. Okay. So there is also a factor of 1 by 2 factorial. So this is equal to, if you had put the whole value, you would have got x plus h whole square. So you see, this is an exact statement. There is no approximation. H can be any quantity. H need not be small. Approximation comes when you truncate the series. If you know all the derivatives at a point, you can write an exact statement. Like in the case of a polynomial, you know all the derivatives, so you could write an exact statement. Approximation will be when you truncate. Then it is good when h is small. All right. So same thing is happening to this velocity. Now this velocity is a function of position and time. So how do you find dv? All right. So first derivative with x into whatever is the change in position dx, change in y coordinate, change in z coordinate. Now what is this dx? Your particle was initially here. After time delta t it goes here. So what is this change in this x coordinate? It will be x component of velocity. Suppose your velocity x component is v1 into delta t. That will be the change in x coordinate. What will be the change in y coordinate of the particle? v2 delta t. Can you see this? Yes. So this one is equal to, this one is equal to, so your velocity is basically v1, v2, v3, three components. All right. So this you can write as del v by del t So you divide by delta t on both the sides. So this becomes acceleration of that particle, which went from here to here. It is acceleration of that particle which went from here to here. Only description of its velocity was spatial. So this you write as del v by del t plus this you can write as can you see this what I have done? I have written this as a dot product of these two vectors. Del v by del x. So this is having a dot product with v1, v2, v3. This is nothing but gradient of v. You know gradient operator?
No, sir.
This is known as gradient operator. So this is nothing but del by del x. Okay. So I just did gradient of v. So this thing, whole thing with v. So you will take del by del x of v, del by del y of v, del by del z of v. Okay. And this is having a that multiplication with vector v. This is nothing but vector v, velocity vector. So this is known as convective part of the acceleration. And this is known as local time derivative. So a particle has gone from here to here. So whatever is a change because of this change in position is the convective part. And whatever is the change in velocity due to because of the difference in time, this particle has changed its velocity by a local time derivative, that is its local acceleration, and this is the convective acceleration. So you go through it again. I will be putting the recording so that you understand. If you play it again, you will understand it better. So this term has appeared because you have done a spatial description of velocity. You are given velocity as a function of space and time. Particle was here, it acquires this velocity. Particle comes to this position, it acquires the velocity corresponding to this position. Now we'll take a simple example. Suppose you have a particle in space going around in a circle. So this is my x coordinate, y coordinate. This is my position vector of the particle. So what is my particle? X, y. Suppose particle is going around in a plane. So this is the position vector of the particle. Now it is going around with an angular velocity omega about z-axis. So what is its velocity? You know velocity of this particle A? You must have heard of omega cross r. So I, j, k, 0, 0, omega. Suppose angular velocity is omega k. And what is your r? Okay. So if you expand this, what do you get? I into minus y omega, j into minus x omega, so you get minus omega y in I plus omega xj. This is the velocity. Also, you know velocity is tangential to this path. So you can also say velocity is equal to omega r tangential vector. What is this radial vector? We call it ER. Tangential vector, we call it E theta or E tangential. So what is ER? If this angle is theta, your ER is cos theta, sin theta. What is the E tangential? Cos 90 plus theta, sin 90 plus theta. This angle is theta. This is further 90 degrees, so 90 plus theta. So this becomes minus sin theta, cos theta. So your velocity becomes omega r minus sin theta, cos theta, same as minus omega y, omega x. So this is velocity of the particle. You assume it is in the xy plane. So third coordinate is 0. So you are given velocity as a function of position. Now instead of a particle going around in a circle, you assume it is a full body. It is going around rotating about this axis, about z axis. So any particle in space will acquire the velocity of this description. You've got different positions, so they'll have velocities corresponding to this. Suppose I want this is going around with an angular velocity omega, constant angular velocity. So it means it is not a function of time. So this velocity is not a function of time. So how do you find acceleration? So I use this, derived this expression before. Now I want gradient of v. What is gradient of v? If you just look at it, it is this is known as gradient operator. If you take gradient of velocity, it will look like this. If you just expand it, you can write it as vi comma j. So comma means derivative. So Einstein introduced this nomenclature, this description. So I comma j. So you see j is the like a column index. So when your j is 1, you have derivative with x1. When your j is 2, you have derivative with x2. When you have j equal to 3, your derivative with x3. And v1, v2, v3 are components. I is 1, 2, 3. So this is the way your matrix will look like. So if you look at this description of the velocity, your v1 is minus omega y. So what is del v1 by del x1? 0. Del v1 by del x2 minus omega. This is 0. Now this is your second component of velocity v2. Its derivative with x is omega. Derivative with y is 0. This is 0. And this third component is anyway 0. Now we have to multiply gradient of v with v. So your this matrix is 0 minus omega, omega 0, 0, 0, 0, 0, 0. This you have to multiply with velocity vector minus omega y, omega x 0. What do you get if you multiply 0 with this minus omega square x? This with minus omega square y. So this is, you get a vector. You are multiplying a matrix with a vector, you get a vector as the output. So you see your dv by dt. So this we found using Eulerian mechanics. If you look at the particle going around in a circle, what is its acceleration? Centripetal acceleration. And what is the formula of centripetal application? Acceleration omega square r. It is pointing towards the center. This is your ER. So the direction is minus ER. So you get minus omega square r. ER I told you is cos theta sin theta. So you get minus So you're getting the same answer as before. So this you did by Lagrangian mechanics. You followed the particle motion, you found the acceleration using Lagrangian mechanics. You know centripetal acceleration is omega cross r. So we found the acceleration of particle using Eulerian approach and Lagrangian approach. So this thing will come handy later on when we will go further in this course. So how to find absolute time derivative if the description is spatial or Eulerian. So that is what we did today. We found this expression del E by del T plus this is dV by dt. We found acceleration of a particle. This is total time derivative. So we'll continue with it. If you have any questions, you can tell me.